The Simatic software offers a wide choice of programming languages that support you in the implementation phase of a plant's life cycle. The basic package includes the ladder, FBD and SCL languages. The options available include the programming languages S7 Graph and S7 SCL. Each of these languages is in compliance with the IEC 61131-3 standard and is based on a specific language concept. Whereas programming with STL is hardware-oriented based on statement lists, with ladder, FBD and S7 Graph, it is possible to interconnect graphical elements. S7 SCL is a programming language that is similar in syntax to the easy-to-use high-level language Pascal. From these various languages, therefore, it is possible to select the language most suitable for each task to be mastered in an automation plant and thus keep time and costs down to a minimum. In principle, all automation tasks can be solved with ladder, FBD and STL. However, they are best suited for controlled tasks. S7 Graph, the graphics programming language, is a great help in creating sequences. Thanks to the higher language constructs supplied with it, S7 SCL is suitable for calculations and data management algorithms. All partial solutions implemented in these languages are compiled in Step 7 blocks. This makes it possible to combine all the partial solutions. By employing these three languages appropriately, you can significantly reduce the implementation time. Taking a simple example, we will show you how you can combine blocks created with S7 SCL with blocks created in the basic languages. What we have to do now is realize a data management algorithm. Using the S7 SCL editor, the functionality is implemented in so-called S7 SCL sources. Here you can use function calls to access existing user blocks, the block library supplied, and system blocks that are already available. Due to the universal database integrated in Step 7, it is possible to have read and write access at any time from the S7 SCL program to the entire tag management of the CPU. This can be done both with absolute addressing and symbolically using the symbol table. Once the algorithm has been implemented in one or more S7 SCL sources, the built-in S7 SCL compiler now generates one or more Step 7 blocks. In this way, a control program written in one of the basic languages can implement the following call hierarchy, for example. The algorithm implemented in FB2 can thus be used repeatedly and its behavior influenced by transferring the relevant parameters. By combining blocks that fulfill specific functions in a precise way, you can greatly reduce the development time. Now you can see why S7 SCL is predestined for complex tasks in the field of data processing. In a sample case, data is to be copied from a source array into a temporary single variable. Each element of the source array consists of a user-defined structure that includes one real, one word, and one string data type. In STL, such a task would require one block call and an index calculation via a memory word. With S7 SCL, you can realize this task with just one line, because S7 SCL has an index operator and an assignment operator. So by using the assignment operator, you can copy complete structures with just one statement. Especially in the case of arrays, you often have to run iterations in order to find, read out, or manipulate a specific element. In STL, only the loop command, which also needs code lines in addition, is available for this. S7 SCL, on the other hand, provides multiple loop constructs. With the for loop, for example, you can set the start and end index of the run, as well as the step size in one line of code. Even loops in which the number of steps is not known during implementation can be realized in just one line with the while and the repeat until loops. So with S7 SCL, it is easier and clearer to create program code, especially for data management tasks. This minimizes a great source of errors and therefore also costs. To demonstrate the benefits of S7 SCL with a concrete example, we will show you the implementation of a sorting algorithm with S7 SCL. The starting point is an S7-400 station as data collector and a series of substations. The substations send data measured at different times to the data collector. One of the tasks of the data collector now is to sort the measured data with respect to the time of measurement in order to enable further data processing. The function should also return a status in addition to sorting. So that the sorting function can be used for any data array, the data array is transferred via the parameter interface of the block. In order to implement a sorting function, you should first develop the underlying algorithm. Sorting algorithms are best visualized taking the example of an index card file box. There are 6 unsorted index cards in a card file box. You first look for the card with the last letter in alphabetical order. In our example, therefore, the card with Y. You now swap this card with the card in the last position. Now the card file box has only 5 unsorted index cards. From the remaining unsorted cards, you now look again for the card with the last letter in alphabetical order, and put this at the end of the remaining unsorted cards. Since the T is at the end, you don't have to swap in this case, because it is already in its end position. Now you continue by swapping the K with the B. Then you swap the G card with the A card. Since the A and B cards are already in the correct order, you don't have to swap them. Now the number of unsorted index cards is down to 1, so they are sorted. You can now easily create a program flowchart based on this algorithm. As long as the size of the unsorted subarray is greater than 1, do the following. Note the index and the current value. Find the maximum in the subarray. If the maximum is in front of the current value, then swap the two values. The size of the unsorted subarray has now been decreased by 1. Start over again. Now the function can be implemented on the basis of this program flowchart. First of all, you create an S7 SCL source in the source container of the Step 7 program, and then open it with a double click. You can create the necessary code structure very quickly by using the development environment. The code generator automatically generates the code lines required for an FC. The interface of the FC has already been defined conceptually. The array to be sorted is a gateway parameter. Furthermore, a status should be returned. Now we have to implement the sorting algorithm. We will proceed from the outside in. We first create the external for loop and fill this with the necessary variables. Since the entire array is to be seen as unsorted at the beginning, you have to select the appropriate run parameter. Index 1, therefore, must be run here from the upper bound of the array to 1. In this case, the constant max size is the upper bound of the array. The current structure element and the current index can each be marked with one line of code using the assignment operator. Now you need another for loop to find the maximum in the unsorted subarray. This loop starts at the beginning of the array and goes to the end of the unsorted subarray. Index 2, therefore, must run from 0 to index 1 minus 1. You can now use an if statement to determine the value and position of the maximum. Finally, you have to check whether the maximum found is in front of the current value. If it is, then the values have to be swapped. If not, then the maximum is already at the end of the unsorted subarray. The core code lines of the algorithm have thus been implemented. In order to obtain a program with correct syntax, you simply have to add the missing variable declarations. The compiler is now triggered to check the syntax of the S7 SCL source. Any errors are displayed in the output window. You simply double-click the error message to jump to the error location. In this case, a semicolon was missing. Once you have corrected the error, you start the compiler again and the Step 7 block is generated. Now this block can be called multiple times by another block or even by another S7 SCL source. The functionality should now be checked online, because often errors are only discovered during runtime. First, the S7 SCL block is loaded into the automation system. S7 SCL gives you two options for checking the functionality: program status and single step mode to monitor variable assignment step by step. To monitor the program status, you simply click on the spectacles icon. In this way, variable assignments that occur during the block run can be observed online on the CPU. This is useful above all in finite state machines where statuses last for several cycles. With this function, however, you can't see very much, because the changes happen so quickly. In the case of highly dynamic processes, like the one we have here, it is best to use the single-step mode with breakpoints. In just a couple of clicks, the controller will interrupt the cyclical operation at the breakpoints. By going through the code step by step, you can have the contents of each variable on the CPU displayed. The error search is simplified considerably in this way, making it possible to do simple module tests beforehand with S7 PLC Sim, for example. This reduces even more the risk of having to change the code on the plant and can thus shorten the commissioning phase enormously. In conclusion, you can see that the sum of the options put at your disposal by S7 SCL enables you to minimize costs considerably.